1.2 says to us, a person stands on a bathroom scale that is fixed to the floor of a lift as shown in the diagram below. Okay, let us understand the scenario. So there's a person on a bathroom scale in a lift. So this is the person in a lift. I'm not going to draw them perfectly, of course. So there's the person on a lift, and of course here we have a scale. So I'm just going to be like, this thing that I have actually bolded here is the scale, right? So they are in a lift. I'm not going to draw the other side because I want to explain something, right? So this is the person in a lift, and this lift, of course, is going to go either up or down. So it might actually go up or it might actually go down. We don't know what its motion is, right? We're just trying to understand the scenario. So this is the scenario that we have. Keep in mind that the lift, we have the lift here. Keep in mind that the lift, the person, the lift, the person, and the scale is one, okay? And the scale is one item. So this is one item. It's a system. It's one system. So I'm going to consider them a single system. I hope that you understand that, right? So what else do others say? They sent us the reading on the scale is largest when the lift moves. Okay, they want us to determine the reading when the reading on the scale is going to be the largest. They want us to determine when the reading on the scale is going to be the largest. So is it when it is going up at a constant speed, when it is going down at a constant speed, when it's going up at an increasing speed, or when it's going down at an increasing speed? So let us manipulate, or not actually manipulate, let us try to analyze our scenario here, right? So let us assume that it is going at a constant speed initially. So it is going at a constant speed. So how many forces? Because we're referring to the person is the one is the one which the scale is going to be reading the weight, right? So let us refer to our person here as the reference, right? So let us assume firstly that, of course, we're going to assume the scenario when it is going up at a constant speed. I mean, when it is going at a constant speed, and initially we're going to start with the up. So if the lift is going up at a constant speed, what is happening? How many forces are acting on this person? We know that, of course, the weight is going to be acting on this person. So we have the weight, which is the gravitational force. So if you draw everybody diagram of the forces that are going to be acting on this person, it's going to be the weight, of course. The forces, the weight is always acting down, but we also have the normal force that's going to be acting on this person. We also have the normal force because they're standing on a horizontal surface, which is the lift, right? So there are two forces that are going to be acting on this person, and of course the lift has maybe a motor. They have a motor, or what is it? A motor, a what? Or an engine that actually or maybe that lift cable. You know what I'm saying? There's gonna be a force that's going to pull this lift up. There's not like this lift is not going to go up by itself. Of course, I'm gonna spend too much time on the whole question because I'm explaining. When you get to when you are in exam, you're not gonna be doing what I'm doing right now. That is why I'm going to be spending more time. All right. So please don't mind me at all. I'm just trying to make sure that you understand the whole question. Right. When you get to the question yourself, you're going to spend this time. Right. So there are two forces that are going to be acting on this person as the lift goes up. Right. But how does this lift go up? It goes up because there's a force that's going to pull it up, which is maybe the force of the motor of the lift, or maybe it is actually the engine. I'm not even sure. It doesn't even matter, right? It is either the motor or the engine that's going to keep this lift going up at a constant velocity. But because it is going up at a constant speed or velocity, that means that the F net is equal to 0. Right, according to Newton's second law, the F net is equal to 0. So we have the net force equal to 0. Now that we know that the F net is equal to 0 because it is not accelerating, it's going up at a constant speed, we have two forces that are acting. That means these two forces are going to be acting in opposite directions, but they're going to have the same magnitude because they have to cancel each other out because the net force is equal to 0. That means that all the forces are in equilibrium. In equilibrium because of the constant speed. I hope that makes sense. That means that this simply means that the normal force plus the negative weight is equal to 0 because they're acting opposite directions. That's why I said negative weight, right? That means that the normal force is equal to weight, right? So because the normal force is equal to weight, what is going to be the reading on the scale? The reading on the scale is going to be this normal force, all right? It's going to be of this normal force, right? So if the normal force is equal to the weight, we know that weight is equal to mg, and then m is constant because the weight of the not actually the weight, the mass of the person is not going to change unless he's eating in the lift and he's gaining weight. Is actually doing that. I mean, he's gaining mass, right? So of course his mass is going to remain constant, and then of course the gravitational acceleration never changes. So that means that the weight is going to remain constant and the weight is equal to the normal force. So that means that when it is going up at a constant velocity, his weight is going to be his mass multiplied by the gravitational acceleration, which is 9.8. Right. Let us check when it's going down at a constant speed. When it's going down at a constant speed, I feel like the same thing is going to be happening because, of course, it is going at a constant velocity. That means that there's no acceleration and the F net is going to be equal to 0. We're going to have the same scenario because of the constant velocity. So that means we're going to have the same scenario, and the net is really going to change. That means that the reading on the scale is going to be mg, which is his mass and also the gravitational acceleration. Right. But what about when it is not going at a constant speed? Maybe it is going at an increasing speed, like we have the options in this question. Let us start with the up at an increasing speed. Let us start with the up at an increasing speed. So if the speed is increasing, the speed is not remaining constant, the speed is increasing, that means that this lift is accelerating. This lift is accelerating. So if it is accelerating, that means that the F net is not equal to 0. The F net is not equal to 0. So if the F net is not equal to 0, and then the lift is going up, it is going up. How many forces are going to be acting up? It is going to be the normal force. We're going to have the normal force acting up. Of course, we have the normal force acting up, right? And we also have the weight acting down. It always acts down, right? But I said that there's a force that is going to keep this lift going up. It's either the force that is applied by the motor or the engine, right? But because it is not actually going up at a constant velocity, that means that force is going to be causing an effect, right? That effect is going to be causing the lift to accelerate, right? So that force is going to be causing an effect, and we're going to call that force just F, or FA, as a lot of students are used to it, force applied, right? Right. So that means that the forces that are going to be acting up are going to be the normal force plus that force that is applied by the motor or engine, right? So that means that the reading on the scale is going to be, now it is going to be, we have the F net is equal to, well, it's not actually equal to 0, right? So that means that F net is actually greater than 0. So let me just say greater than 0. And then we have the normal force plus that force, I'm just going to call it F, maybe A, and then minus weight is greater than 0. That means now the net force plus the FA, which is the force applied, is greater than weight. Is greater than weight, right? So the reading on the scale, remember what the reading on the scale is. The reading on the scale is the weight of the person, right? So if the weight of the person is going to be greater, it is going to be less than this, that means that this thing is going to be greater than the weight of the person. This is the original weight of the person. Remember that this is mg, which is the original weight of the person. So that means that that original weight is going to be less than the normal force plus the force applied. That means that this weight is going to be greater. That means that the reading on the scale is going to be greater. Remember that this is the reading on the scale. The reading on the scale is going to be greater than his or her normal weight. His or her normal weight is m multiplied by g. That is the normal weight, right? Right. But the reading on the scale is going to be greater than that normal weight of the person. That means that the reading on the scale is going to be largest when the lift is going up at an increasing speed. I hope that makes sense, right? So that means that the correct answer here is going to be A. Not A. What am I saying? The correct answer is going to be C. So the correct answer for 1.2 is C. That is the correct answer, because the reading on the scale is going to be greater than the normal weight of the person. Oh my god. This is let me do this. So sorry about that. Okay. Right, let us get to 1.3. So the correct answer for 1.2 is C, which says that the largest reading on the scale is going to be when the lift is going up at an increasing speed. Now let us go to 1.3. 1.3